Hi everyone, I'm Shiyu. So welcome to the lecture 4. In this lecture, I'm very happy to share the GPU acceleration feature of Perturbo, which we have released in last December. So this work is done with the engineer Dolly Pinkerston and some other group members. So this short lecture consists of 2 parts. First, I will do a slide presentation on the data structure, the algorithms, and also the benchmarks. At the end, I will move on to the permanent cluster at NERSC to briefly show how to compile the code. Okay, let's get started. So I will start with the Boltzmann transport equation. But actually, the GPU feature can support both the transport and ultra-fast dynamics. So here, I will take the dynamics, for example. As we all know that the core part of the BT approach is the collision integrals, which I show here. As we can see from this formula, so each element of the collision integrals can be obtained by a summation over a lot of scattering terms. So each scattering process can be also called as a scattering channel, which describes that an electron in an initial electronic state Nk goes into the final electronic state Mk plus Q by absorbing or emitting a phonon nu Q. So there are 2 reasons why such a calculation is very expensive. So first, the number of the scattering channels could be as large as 10 to 8 or 10 to 9 in a typical calculation. And second, we needed to do a time stepping for the dynamics, while the total number of steps could be more than 1,000. For each step, you needed to do expensive integral calculations. On the other hand, nowadays, more and more supercomputer centers are equipped with advanced GPU chips. Taking the permanent cluster at NERSC, for example, more than 1/3 of the nodes are GPU nodes. So we think the time is ripe to leverage GPU for the intensive electron phonon calculations. So next, I will talk a bit more about the scattering channels and the electron phonon coupling matrix. So the left plot shows the electron phonon coupling G matrix, which is a 5-rank tensor. It's the core part of the core ingredient of the formula I show in the previous slide. We can get this quantity from first principles. However, in a typical calculation of the electron phonon calculations, we will always set a narrow energy window, as I show in the band structure plot, around the states of our interest. So only the scattering channels in this energy window will be considered in the calculations. Also, some scattering channels whose magnitude less than the threshold will be truncated in the calculation, resulting in the final scattering channels. The valid scattering channels are scattered in the G matrix, which means they are very sparse. So it's very challenging to figure out an efficient way to store the elements. So let's move on to the right plot. So each scattering channel, as we introduced before, can be nabbed by the momentum and the band index and the phonon modes, say the Nk, Mk plus Q, and the nu Q, right? In the older version, such scattering channels could be grouped in such a way. We group all the scattering channels which corresponds to the same momentum together in a sub-array. However, in the new version, we could treat them equivalently and store all the scattering channels in only one large flat array. Let me try to explain it more clearly in the table format. So the figure on the top is for the previous implementation. So each line corresponds to each KQ pair, and all the scattering channels corresponds to this same momentum will be stored in these sub-arrays. They will connect to each other by pointers. So finally, we will have a lot of sub-arrays. But in CPU, this data structure is very elegant and very convenient because it exactly follows the object-oriented programming. And also, as you know, that in the electrophonon codes, sometimes we need to manipulate the individual electronic states and phonon states. So it's very convenient. However, it's not that friendly if we want to extend our code to the GPU. Because so many subarrays will cause the significant I/O overhead to the GPU. And instead, for the GPU, we store all the scattering channels in only one large flat array. So it's very convenient for the GPU to access the data, and it's also very efficient for us to utilize the high throughput computation ability of the GPU. But it's not enough for you to only have the good data structure. You should take care of the parallelization, which is also a big difference between the CPU and the GPU. So let's look at this single element of the collision integral matrix. So previously, each element will be contributed by different scattering channels, which will probably computed on different CPU processes or OpenMP threads. It's totally okay for CPU, but it's very bad for GPU. Because if different threads are accessing the same element or updating the same element of the collision integral matrix, the synchronization across CUDA cores, CUDA threads will be significant. So in the new version, we create an additional layer. We call it a target layer. So let's focus on the red 9 arrows. So each element of the collision integral matrix will be contributed by the same group. We call it a target. And all the scattering channels which will contribute to the same element of the collision integral matrix will be grouped together into this group. So finally, each element of the collision integral matrix will be updated by only target and then by only one CUDA thread. So in this way, we can avoid the synchronization across the CUDA threads. So the cost is that we need to do a setup step at the beginning. However, we only need to do once at the very beginning of the calculation for the whole calculation. And this method is very general, can be extended to other scattering mechanisms like the electron scatterings and also the electron defect scatterings. Okay, as I mentioned before, all the calculation modes of the transport, the M sigma, the trans-RT, IT, also the magneto transport, as well as the ultra-fast dynamics are supported by such an efficient GPU feature. We implement this feature by using the OpenACC. We have performed a very thorough benchmarks on different systems covering different scenarios, such as box systems, 2D systems, the system with and without spillover coupling, and the metallic phase and also the semiconducting phase. All the calculations are performed on the GPU nodes at NERSC. Each node is equipped with 64 CPU cores and 4 A100 GPU chips. For the benchmarks, we will first show the memory usage. The left histograms means the CPU, and the red one is for GPU. The blue one is for dynamics, red one is for transport. As we can see from this figure, the dynamics consumes even less memory than the CPU one, while the transport consumes a bit more memory. The reason is that for transport, we have an additional loop, which is for the directions of the external field for the linear response theory. For CPU, we will just do the iterations over each directions. However, for GPU, we store all the data for different directions in the memory to get better performance. And then for the performance analysis, the left plot shows the speed up data. So compared with the CPU one, we can see that the dynamics can get overall around 35 times speed up, while the transport can get even larger, more than 40 times speed up. The right plot shows the apples to apples comparison. Instead of comparing with the previous old version, we compare the GPU code with OpenACC and the GPU code without OpenACC. So the code is exactly the same, but the only difference is whether the code is running on the CPU or GPU. As we can see from this figure, compared with the one without OpenACC, which are shown as blue histograms, the one with OpenACC could get a similar speed up as we showed in the left plot. Finally, we will show the scaling performance. Here, we only show the strong scaling, which means we keep the material size the same, but we increase the resources, which is the number of the GPU nodes. We highlight the common scenarios for most users by shading. So as we can see from this figure, it exhibits near ideal scaling up to 20 nodes for dynamics and with a slight decrease for transport. Okay, that's all for the slides presentation. So next I will move to the permanent cluster. We also prepared a markdown file for your reference. So if you happen to have access to the permanent cluster, you can follow this tutorial. Okay, I already logged into the permanent cluster. Okay, let me go out of the folder. So the most important thing, and also the first step to compile a code on a HPC cluster is the environment. So here we provide well-optimized compositions of the packages of the libraries. They should be compatible with each other. If you want to change one of them, you probably need to change the remaining ones. So here I will just follow this and copy and then paste. So basically, these commands help us know the correct CUDA environment, the NVIDIA compiler, and the math libraries, and also the HTF5 and the FFTW libraries. which are essential ingredients for a compilation of the QE and the Perturbo. So I have already compiled the QE code just to save our time. So, but we will also provide the recipe here. You can just follow them. We will directly go to the Perturbo step. Let me try to remember this. So first step is to git clone the Perturbo wrapper. And enter this folder. And then copy this configuration files. Okay, let's open this file. I will briefly explain the flags. So for the compilation of the Perturbo, either for the CPU version or for the GPU version, either for the older version or for the new version, we need some ingredients from the QE Quantum Espresso packages. For example, here we need it's the configuration files. These two lines, I think, is very basic flags for the compilation of a GPU code with NVIDIA compiler. And these two variables, two flags, are very important. So basically, by default, the NVIDIA Fortran compiler just support the variables less than 2 gigabytes. But for typical electron photon calculations, a variable larger than 2 gigabytes is very common. So we need to turn on this feature. And then as what we show here in the comments, the managed which is a unified memory, CUDA unified memory, is not supported in the parameter. So we need to turn off this data structure. And also the other important one is a zero init. We need to let the compiler know that to initialize some variables as zero during the compilation processes. And these two variables are very common for the standard compilation with the NVIDIA Fortran compiler for the GPU version. The CC80 corresponds to the hardware, the GPU hardware, which you will use. And this is to turn on the ACC functionality. If you just want to compile the code with NVIDIA compiler, but for a CPU version, you can comment out these two lines, but uncomment these two lines. Okay. So for the other flags, I suggest you to keep them as what they are. Here is HDF5. If this global environment variable doesn't work, you can change it to the absolute path. Okay, we are all set, and we can compare the code. It's very simple. You just need to type make. Okay, from this line, you can see the compiler is actually compiling GPU code from the prompts from the screen. Let's take a break while watching at the screen. By with this simple demonstration, our goal is that to want to give you a sense that the GPU feature of Perturbo is very useful and is very easy to use, to compile. So hope it will help you with your daily research. Okay, now it's compiling the Perturbo.x. I think it will finish soon. Okay, so it finished. I check the executables. You can check whether the linking information is correct. As we can see from the outputs, the code is actually linked to the CUDA libraries. So I think it's successful. Okay. So though we demonstrate on the permanent cluster, you can adapt this configure file based on your own HPC environment. So basically, I don't think you will change too much this file, but you probably need to take care of the environments. This is probably different on your own HPC. Okay, so that's all for this lecture, and I will briefly show how to use the GPU feature in the typical transport calculation in hands-on session 4. Okay, I'm ready to take any questions.